Hello everybody, good evening, good morning, good afternoon, wherever you are in the world. Welcome to the first live stream from the 2021 edition of Cosmology from Home, the cosmology conference that we're doing these 2 weeks, which takes place entirely online from the comfort of our own homes. We're here to tell you about what's been happening in the first 2 days of this conference. Just so everybody knows who I am, my name is Deanna Hooper and I'm a postdoctoral researcher currently at the ULB over in Belgium. I study the universe, the contents of the universe, fun stuff like dark matter. I'm a participant at this conference and I'll also be giving one of the plenary talks here. So today we're here to talk about this conference, what's been happening in the first few days, and just give you our general thoughts about how everything's going so far. So let me welcome to screen my fellow conference participants who are all going to help me describe what's been going on in the first week, and I should unmute everybody. Okay, hello everybody, welcome. You're all on screen now.
Hello Deanna, hello other participants and hello audience.
Great to have everybody here. Everybody joining, thank you for joining. Hey, Ange, Christian, Walt, nice to see you all. Thank you for stopping by. Molly, great to see you. Some of my regulars here as well. Hopefully we'll branch out and catch other audiences today as well. So I already introduced myself, so let's just get through some introductions to figure out everyone we have here on screen. Hey, Pablo, Paul, thank you for joining. So let's go around clockwise. So I've introduced myself. So Angaran, do you want to introduce yourself?
Hi, everybody. Nice to be on this interesting video. So yeah, I'm a PhD student in theoretical physics. I work on all things cosmology. So I try to use cosmology as a way to understand some of the really cool phenomena like quantum gravity and stuff. So yeah.
Nice, great to have you here. So far we have postdoc, PhD. Sean, over to you.
Hi, yeah, I'm also a postdoc, part-time postdoc and part-time business person trying to make money out of, well, trying to share research with the general public through apps and videos and things. My research side of things, I've bounced around a lot within cosmology, but at the moment, the stuff I'm actively working on is how these things called primordial black holes might form in the early universe, black holes being super dense regions of the universe that light can't escape from, and primordial meaning formed very, 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 very early in the Big Bang.
Nice, looking forward to hearing more about that. Okay, Rachel, do you want to introduce yourself?
Yeah, hi, my name is Rachel Beaton. I am a postdoc at Princeton University and Carnegie Observatories, but I'm located in Princeton, New Jersey. And my primary field of research is using stars and stellar populations to measure distances that we use in cosmology for lots of different reasons. But at this conference, I'm talking about the Hubble constant, which is the expansion rate of the universe.
Which is a topic who anybody who follows my broadcast has probably heard us discuss quite a lot because it's a very hot topic in the field currently. So thank you for all the awards, everybody. We really appreciate the awards, and thank you for the high five award, Pablo. So we mentioned here PhDs, postdocs all across the world. We're juggling 4 different time zones for this stream. For me, it's a very convenient time, 8 p.m. I believe the most inconvenient one is Sean. It's 6 a.m. in the morning for you, right?
Yeah, I forgot to mention that. I was going to ask for your sympathy that if I forget anything or look drowsy at 6 a.m., but I forgot to mention that. So that's mistake number 1.
Yeah, I think, you have a good excuse. It's 6 o'clock in the morning. I'm not sure if I would get up so early for a live stream. So we appreciate you juggling your time zone to fit in with all of us.
No problem.
So we're all attending this 2-week-long conference that started yesterday and is going to last all of this week, all of next week. We have between 300 and 400 participants, and it's really, really great fun. But I'm not one of the conference organizers. I'm a conference participant, I'm a speaker, but I'm not the organizer. But one of the people here is an organizer. So Sean, do you want to tell us a bit about the conference, what we're doing here, how this all came together?
Yeah, so the main purpose of conferences themselves is a chance for cosmologists or researchers to come together and talk like in real time about the research. Obviously, the main kind of way that research is shared is via papers. So you write a document, we read each other's documents, but it's a very slow form of communication. It's a very much more precise form of communication. People take a lot of care over the documents, but it's very slow. So you also want this more rapid form of communication. So that's what conferences are for. We also have all of these wonderful online tools. So the idea was to try and to bring that kind of conference experience into the online world. The idea actually predated COVID, but then COVID made this a much, much more pertinent thing, I suppose. So lots of online conferences now exist that have kind of copy and pasted the real in-person experience into the online thing. And for various reasons, that doesn't work super well, because lots of factors that I can go into in more detail, although I think we should move on to the physics relatively quickly because that's the more interesting stuff for you, the audience. But lots of things don't carry over super well. So the main thing we tried to deal with in this is this thing that the people in research would call Zoom fatigue, where you just sit in front of a screen in a Zoom meeting for hours and hours and hours and hours and hours. So the main way we've tried to overcome that, and I guess my fellow panelists here today can say how well we've done that, is by having the talks pre-recorded, the talks of people talking about their research. And then the crucial thing that I think most other conferences miss is also pre-watched, so that you can just watch it in your own time. Like I watch some of the talks while I'm cooking dinner or doing the dishes, and then you literally only come to the screen to talk to each other. You're not sitting there passively watching someone talk. And the other advantage of having it pre-watched is that if it's going too slowly, you can just make the talk 2 times speed. And if it's too difficult, you can pause it and then just stop and like look up terms and things like that. And then the second kind of maybe innovative thing is to use a virtual office space, so that when people are doing a live discussion with each other, you can see lots of different pockets of people discussing inside this virtual office space. And if you want to join a conversation, you can freely move around it. Whereas if you literally just have Zoom or Hangouts or Skype or whatever, there's just the one discussion, maybe with a few breakaway rooms, but it's not quite so native to be moving between the spaces. So I would be keen to hear what my other panelists here today think about that.
So I completely love the format. This conference was done the first time last year and I had to miss most of it, but from what I joined last year, it was fun. But this year heading into it, I really had the pre-conference excitement that I don't get for online conferences. Just the idea of pre-watching talks, it makes so much sense. Like I can pause a talk, go off, get coffee, think about what I've just heard about, digest it before I move into the next part of the talk. Makes it so much easier. And just moving around our virtual space, which they've given us a beach setup. We have pools and sunrise beaches and dolphins and fire pits. Definitely not conducive to working, but it's nice because you just walk around here and see people you might know and go chat to them, see other people you don't know and just wander over like, hey, what are you guys chatting about? It really feels more like an in-person conference. And I think it's the most in-person conference, online conference I've attended. It really does encapsulate that in-person experience to me. I'd love to hear what others have to say about it too. Of course, we can't be too critical with one of the organizers on screen. So Rachel, Engeran, any comments from you?
Be honest, because then we can improve things.
So I'm actually pretty bad about listening to talks in my own time, but I think that's just my own personal discipline. But I like the idea of them being there, so that maybe even if I don't have time this week, I could sit down and watch them later. And we have these interactive tools where if I want to get in touch with the lead author or one of the collaborators, I can do that as well, sort of on my own time. I'm in the middle of a busy time where we're preparing a big data release, so my time is not my own at the level. But it is nice I like a conference because you can do many things at the same, which is often very helpful. And I feel like I'm doing a better job balancing that than I would if I were in person.
Engeran, any comments about the conference formats?
Yeah, no, I find the conference format very like smart, and trying to think of the right words. Why am I going blank? I don't have the same excuse as you, Sean, for a bad time zone. But yeah,
my tiredness is permeating through the connection and overcoming
yeah, some sort of osmosis. But yeah, it's very innovative in how it's given an opportunity for academics in various stages of the academic cycles. No, cycles are wrong, but yeah, like academic hierarchy. I don't like using that word, but yeah. But yeah, we've been able to have plenary discussions on people who are experts in specific fields, and we've also been so these would generally be very senior postdocs or professors potentially, and for the students that we have the opportunity to engage in these parallel discussions, and I think that's it's great because these parallel discussions are generally shorter talks. So one, it puts less pressure on the students, or I don't know, maybe some students find shorter talks more pressurized, but it also gives more students the opportunity to share their work and engage with more senior people who can give their own sort of expert opinions on these fields that they've obviously come to learn a lot more about because they've been in the field for longer. And I think that's a great aspect of cosmology from home, because it's not necessarily a common thing to find in conferences. I've only participated in so many, but generally speaking, you don't find such a combination of both senior and junior academics in like just in one day, for example, of conference talks. So yeah, I find that quite enriching, I guess.
I will say that one downside of pre-recorded talks, having recorded them, is that it gives you the chance to redo your talk over and over and over and over again. Right? And if you do a live talk, you get ready for it, and then it's over, it's done. If you said something bad, that's it, that's the end of the day. But if you record it and you put one word out of place, then you're thinking, I could re-record the whole thing. Or if you have any video editing skills, you can just record that slide. I have zero editing skills. So I sat there like, do I want to redo it another time because of one word? So that is a slight issue with pre-recording talks, but I think that's more of a me issue than a pre-recorded talk issue.
I think that's an everyone issue, given the fact that we haven't released the second week talks yet, because it's a 2-week conference, and we're literally getting emails from people saying, I've been watching some of the first week talks and I realize I could have done better. Can I please record my talk again and submit it? I just wanted to add one thing. Angaran was mentioning that we have the more established people or something, or I forget the exact terms, giving plenaries. So plenaries are meant to be the kind of more substantial talks and things. And Deanna might not mention it herself, but she is one of the plenary speakers at the conference. So I thought I'd just bring that up while it was on my mind. And the other thing I was going to say is I think online conferences and in-person conferences can have different niches within the community. One of the major advantages of an online one is that literally anyone can come. Our conference fee for the institutes that can pay the fee is 30 euros, which is not very much. But even if you're a PhD student in a country that doesn't have like a institutional support, then we'll waive that conference fee, and then literally it's just whatever you need to get onto the internet that can allow you to come. So that's a huge benefit that we can hear from researchers that are publishing papers, and we're reading their papers, but we very rarely get to talk to. And then no, I've lost my train of thought. So if it comes back, I can repeat say that second thought. But
I also like how we set up these community spaces in Slack, and those exist at the end of the conference. Like there's a way for someone to get in touch with me that I met, even if we didn't write down our email addresses, right? And I've helped, I ran a workshop about a month ago where I still have conversations with some of the researchers who are able to participate in the virtual workshop. And they can ask me questions and I can help with their projects. And that's been really, really rewarding.
Yeah, I think the Cosmology from Home Slack from last year is still open and has been used to organize social events for like 6 or 7 months after the conference. Sorry, Sean, you were about to say something.
I remembered, and I've forgotten again, but I think I'll remember it. I remembered again the thought I wanted to add, which is about the taking a long time to record your talk because it's pre-recorded. So I'm probably going to say something that's a little bit not the mainstream thought, but I think when you're writing a paper, you might like sit down and actually write it for weeks, right? Like I don't mean the actual research. I mean just writing that document that you then share with the research community. You probably take weeks, maybe even months. When recording a talk, we normally just maybe spend a couple of days beforehand making slides and thinking what we're going to say, and then we put it online. But if you look at the best talks from last year's conference and this year's conference, they've got nearly 1,000 views, and they probably also only spent like a week maybe preparing it. I mean, these are some really, really good talks. But if we spend as much time making pre-recorded talks as we do on our papers and use that as a genuine method to share our research with each other, I think it would mean that our papers would have a higher impact because people would be able to digest the paper more easily. So I don't think that's a negative, the fact that you wanted to keep tweaking your talk to make it even better. And I think more people should spend that much time, because that talk then is representative of your research and people will be able to watch it for months, if not years. The same way we look at some classic papers from 50 years ago, we might be looking at some classic talks from 50 years.
Yeah, exactly. It's become more of a norm in the community, actually. So there's a platform that we use as researchers, which is becoming more popular now, called Benti Fields. And Benti Fields gives you the opportunity to actually submit video abstracts. So abstracts are these short intros that we give to kind of summarize what the paper is saying. So if there's somebody who's a bit too busy to go through the whole paper, and a video abstract is something that's becoming more of a common thing for researchers to do. And I think, yeah, as Sean said, these talks could potentially be watched years from now. Like there are lectures which are known to be kind of legendary in at least in the theoretical physics community, which were done maybe even 20 years ago. Like the classic example is going to Feynman's lectures and watching recordings of him. So if you give a very clear talk about a field that you've helped make massive contributions to, which you summarize very well in a talk or series of talks, I think, yeah, they could be a very good resource for students in the future. And then there's the obvious point that like videos kind of, I don't know, they can like overcome a barrier that of sort of absorbing information, and it gives another way for people to access like physics and stuff. Because one thing that actually came up, I think it was Nico, one of the co-organizers, she mentioned how she finds it a lot easier to be able to watch these talks and have the slides accompanying them side by side. It makes it easier just because of the fact that like things like eyesight and stuff can be a limiting factor for people. And I think that's a very important point, that we can improve accessibility to people by sharing our research through other platforms.
It's definitely an interesting point, and it is something we could discuss in depth. But the point of this session, we've introduced the conference, what we're doing. We do want to discuss what's been going on in the conference, apart from listening to pre-recorded talks and recording pre-recorded talks. So we're on day 2. Yesterday was the first day of, we're on day 2. Yesterday was first day, obvious. So on day 1, the biggest event that we had was a panel discussion on the Hubble tension. This was a 1.5 hour long panel session. And Rachel, you were one of the panelists there. So do you want to just give us a brief summary about why we did this panel? What was it about? And why did you think this was an important panel to have?
Yeah, so our panel yesterday was on the tension in the Hubble constant. And right now there are papers where we've measured the Hubble constant directly using the distance scale. So that's where we measure distances to galaxies and the redshifts to galaxies, and you put those together and you get how fast the universe is expanding. And so that's the traditional way to make this measurement. Another way to make this measurement is actually to make measurements of the state of the universe from the cosmic microwave background, and you put those into the standard model that we currently use, and you can get the expansion rate now. And those measurements are somewhere between 3 to 5 sigma in tension, depending on which paper you want to use and which error bars you want to quote. So I'm on one of the teams that works on Team Distance Ladder, and we brought together another person representing the other major team. So the team I represent is led by Wendy Friedman, and then the other major team is led by Adam Rees. And so Dan Skolnick represented that team. He's a professor at Duke University. And then we had 2 folks who are critiquing our work from the community. So Suhal Dawson and Dwan and Benham Javamarty. And so those are two people not in these two major teams, but that are watching us from the sidelines and sort of checking our work in the literature. And so it was really important to have us all sit down and talk together. The topics that we tried to address were, do our two teams actually think that we're reaching agreement, or do we think we're even discordant amongst ourselves? And then we also explain in more depth some of the papers that had been, and make sure everyone at the conference actually had a detailed understanding of some of those criticisms. So that's the panel, and we can follow up on some of those topics as they're interesting.
Christian is asking in the comments if there's a recording of the panels. So Sean, I'll throw that question to you.
The recording there is a recording. It's certainly not available at the moment to anyone but conference participants. It might be made available after the conference, depending on certain factors that maybe I shouldn't go on into live. But if it is made public, then Deanna will know about it and will certainly be able to share it.
Yeah, so some of the plenary talks will for sure be made public after the conference. The rest is not yet clear. For now, it's just available to conference participants. But yeah, it was a super interesting discussion. I think it was really important to bring together both people from these different teams and people who have criticized your work. What I really appreciated here is that the Hubble tension is often phrased as a tension between these local measurements and the CMB. And usually in panels, you bring up somebody from the CMB side, somebody from the local side, and that's it. And this was not about that. There was no CMB involved. I was surprised, no CMB, but it was actually purely people working on these local measurements and just getting this level of agreement. And I think that was a super interesting discussion to have, and just also to see how you all, because you had two people there disagreeing with your work and criticizing your work, but it felt like a very friendly and civil conversation and very constructive conversation. So I'll come back to you in a minute. Rachel. Just want to see if any of the others have any opinions or comments about what was discussed yesterday. Angaran, Sean?
Yeah, sorry, I was just about to reply to Paul in the comments, but just replying to Deanna's thought about this being kind of a unique, interesting discussion, that was certainly what we were going for when we framed exactly who we invited and what we told the panelists to do, that there's a lot of discussion between, as you said, the local people and the CMB people, and it's not actually really clear what a productive discussion between those two groups would look like, given that they're experts on completely different things. And it's like the local people are like, well, the CMB people must have some systematic error somewhere, and the CMB people are like, well, the local people must have some systematic error somewhere. And it's like, okay, they're not experts on each other's work, so it's not. We weren't even clear what a productive discussion would look like, let alone we'd seen one and wanted to emulate it. But then we thought, okay, these local measurements are always, especially the group that Rachel's in, is always kind of brought up as evidence that maybe there isn't a tension because their value is closer to the CMB value. So we thought maybe we can have but on a physics topic, I found it interesting, Rachel, that you said there's a 3 to 5 sigma locally. A lot of people do bring up this tip of the red giant branch measurement, which maybe you can explain in more detail for the audience, as proof that there are local measurements consistent with the CMB. But when I look at your measurement and the CMB measurement, they're not like super consistent. So the fact that there are other, even more inconsistent ones, it doesn't feel like you guys alone would make everything smooth if you were the only people out there. So I'd appreciate your thoughts on that. But please maybe introduce to the audience like how you're measuring it, if you can.
I thought I'd just jump in here. So when we're talking, I think maybe we should clarify when we say CMB, and but yeah. So when we're saying, so when we're talking about these different measurements, so as Deanna said, well, Deanna's kind of described it as sort of local and CMB, but what I've kind of like come to think of them, and I guess the general terminology I've come across is direct and indirect measurements of the Hubble constant. And so when we're saying direct measurements, we're saying we literally have something in the sky, which is the stuff that Rachel does, where she measures how fast how fast the universe is expanding, because of the fact that we've got certain things which are moving far away. So in the case that Sean was just saying, the tip of the red giant branch, those are specific stars, and in the case of the CMB, which just stands for the cosmic microwave background, Diana, I think you just threw it just up on the screen. So yeah, this cosmic microwave background is this thing from the primordial universe that was emitted about 380,000 years after what we call the Big Bang. The Big Bang is just another word for us not knowing what's actually going on. And from this, you can actually infer how fast the universe should be expanding today, i.e. an indirect measurement. And that's just by taking into account all the processes that have been going on in terms of the evolution of the universe from 380,000 years after its birth, in inverted commas, to where it is now. And yeah, I don't want to say too much about where I think the problems lie, because at Cambridge there's definitely a more skewed side in terms of the academics who work on a very specific collaboration, who have their very strong opinion. So I feel like I might shoot myself in the foot here if I go on record to say anything. So yeah, I'll just sort of let Rachel go on to talk about TRGB stuff.
If I may make just two comments before you go on that, Rachel. Me flashing the CMB image is a running joke with everybody on HAPS that I'm incapable of going a broadcast without showing the CMB. So as soon as the word CMB was mentioned, I had to bring up that image. It's just a rule of HAPS now. Just another comment, David is pointing out here in the comments that I did a whole broadcast about the H0 tension a couple of weeks ago. So if you want the full 1 hour version of this, you can go back and find it on my HAPS broadcast. Okay, Rachel, do you want to tell us about the tip of the red giant branch?
Yeah, so the traditional way that folks have gone out and measured the Hubble constant directly has been to use these variable stars called Cepheid type variables. And they were discovered around the turn of the 20th century. Or actually earlier than that, but they were first used to measure distances around the turn of the 20th century by the famous astronomer Henrietta Swan Leavitt, or the newly famous astronomer Henrietta Swan Leavitt, and that's probably a whole other broadcast. But we've basically been using that technique for about a century now to try and make this measurement. And Cepheids are these really powerful tools. They're pulsating stars, and the period of their pulsation is related to their true luminosity. But they're young stars, and they live in sort of the crowded and most complicated environments, just like young people. It's like, little babies are very complicated. Cepheids are also very complicated. And so we tried to do something that was completely different, and in that way had completely different systematic concerns versus than the Cepheids. So systematics are things that bias your measurement. And so we use the tip of the red giant branch. So red giant branch stars are pretty much the exact opposite of Cepheids. They're low mass, old stars. They're very metal poor, and they're extremely boring. And because of those things, they're a great test. However, we started this project about 5 years ago and started completely from scratch. We didn't have a century to sit on to fall back on. So we had to do everything from scratch. And our first real H0 measurement was about 2 years ago, and we came out about 2 sigma consistent. It's like 1.6 to 1.9 sigma consistent with Planck, and about 1.9 to 1.6 consistent with the Cepheid-based measurement that had been the real driving force for this tension for several years. And we think this is really interesting because we have such different systematics than the Cepheid-based route. Oh, there you are. Because it could be saying that some of these systematics do really matter. And the important thing to say, of course, is that I really do think the SHOES team has done a good job. I'm not trying to criticize the team. We're criticizing, or we're not even criticizing. We're saying that the method has these components to it. And if we remove these components from consideration, do we get a slightly different answer? At the same time, our measurement isn't without contention. It's a new technique, which means we don't have, we don't have as much to fall back on. So we're arguing about different things, different choices that we made in our process. And some of those choices are actually at the foundation of the distance ladder, which means we shift everything back and forth. And so that's some of the stuff that we discussed in terms of our controversial bits, is kind of details. And then on the matter of whether there's a tension or not, I think it's hard, right? Because I put out a measurement, or my team puts out a measurement, until someone else verifies that measurement. It's hard to say that I didn't make a mistake. And so I actually see discourse in the literature, when it's framed respectfully, is really important and fundamental to science. It is very, very possible that I made a mistake. I do a lot of the photometry, and I believe I've done my best job, but it's possible that I neglected to consider something, or I didn't know I needed to consider something. And so having independent teams evaluate your work is actually really important. It doesn't feel great all the time, because it's often framed as this battle, but it's fundamental to our process to have these kinds of discussions. And so having one in an environment where we all felt able to be constructive, and I think the selection of the people on the panel was very good, was great. And I felt like I learned a lot more, and I was able to show my respect for my colleagues as well, which I think was really important for them to hear from me.
I think there were two comments that really stood out to me yesterday in the discussion. The first one was when you said that despite the fact that you are doing different approaches, you still do agree remarkably well. There is a slight difference, but you are still within the same overall area. I think it was reiterated several times that you're not really losing sleep over this, because there is still remarkable agreement, even though it's not perfect agreement. There is still remarkable agreement. And another comment that I believe it was you who made yesterday in the panel discussion was that embarrassing errors are now being ruled out. So people are gradually excluding the possibility that one person in the team has made what would be an embarrassing error. I thought that was a really nice way of phrasing it. Like, the obvious things, the embarrassing things are being ruled out. I thought that was a really, really nice phrasing there.
Yeah, I think Dan actually said that, and I probably laughed really loud in the background. But he framed it as it's really good to frame this not as something being right or wrong, but as some component of the analysis being a lot more nuanced and a lot more interesting than we thought it was. So some of the things that we think are quite vanilla terms that maybe we didn't have to think so hard about turn out to be, like creamsicle, Rocky Road, marshmallow flavored ice cream. And we really have to think more carefully about those components. And that's progress, really. It's actually good when you can put forward a piece of work where folks can narrow in on that level. It means you've put it out there in a way that folks aren't fighting over the embarrassing errors. They're fighting over where there's hopefully something to learn.
So I want to throw it over to the other two people here on screen and see if you guys have any thoughts about the panel session yesterday. Sean, I'm not sure if you've had time to catch up with it yet, being 6 a.m. in the morning for you. If you have had time to catch up, it would be great to know if you had any takeaways.
Unfortunately, I haven't had a chance to watch the recording yet. Partially, it's the time zone, so I wasn't there live. But then it's also being an organizer, my time is a little bit occupied. But I'm really looking forward to watching it, and we'll watch it, but haven't had a chance.
Yeah, I think you have two very valid excuses. Okay, so Engoran, let's move over to you. What did you think about the panel session yesterday, if you participated in it or attended it?
I did attend it. It's definitely outside of my area of expertise. I've kept up with the H-naught literature in the sense that I've tried to kind of identify where maybe us as theorists could come in and swoop in and see where we could change the theories to have an effect on the H-naught values that are measured from the CMB. But yeah, it was interesting because like we said, I've never actually seen a discussion between people who've done the local measurements. So that was there's interesting points because that were being made, which I'm just honestly just trying to remember right now. They kind of I guess, like, in terms of the Hubble tension, my gut feeling is that as we did with we had a tension with the Hubble factor a while back, which I can't remember when was this, like a few decades ago, I guess, when there were disparities in terms of predicted Hubble rates, and I feel like yeah, sooner or later it's going to come down to systematics, because I feel like our theories are quite consistent, but there are definitely things that could come in to slightly change things. So prior to this, there was the curvature tension, which was quite publicized. So this is where we discussed us as a cosmology community, the possibility of our universe not being curved but flat, and that kind of was sort of swept under the rug as the Hubble tension gained more fame. So I feel like we will resolve this, and yeah, it's just more about just examining systematics again. But yeah, sorry, I feel like I just gave a very waving my hands answer.
Can I jump in with a thought there, maybe? Like, I know you said that there have been these other tensions that have gone away, and I think most tensions do go away.
Yeah, tensions going away is not the right word. They're not gone away. They've just gone from the public eye, I guess, is the right word.
I mean, the previous Hubble tension went away, right? Like, I think there was
some
measurements coming in at 50, some at 100, and now everyone's kind of converged on the high 60s, low 70s, which is another thing I think that's always useful to mention here when we talk about the tension between the CMB measurement or prediction and the local measurements is just how ridiculous it is that they get so close. Like, it's easy to be honest as a scientist and say, oh, there's this tension, we've got all of these tensions, and then from the outside to be like, oh, these guys are just making it up as they go along. But the CMB made measurements 13.78 billion years ago, and the expansion rate at that point, so the expansion rate squared goes as the density, and the density was 1,000 cubed times smaller then. So the expansion rate was 10 to the power of 9 halves bigger then than it is now, which is an enormously large number. And using the model we have of cosmology about how expansion rates change over time, we can say, okay, it was that big at the CMB. What will it be today? Oh, 67. Well, let's go out and measure it. What is it? And Rachel's group says 69. It's like, what? Like, that's spectacular agreement. And okay, when you look at the error bars, it's slightly different, but we're talking about a 1% error when we've extrapolated a number by 5 orders of magnitude. So there's something that needs fixed there, but this wasn't actually my original point. So I will make my original point eventually, but maybe if you want to reply to my pre-point, go ahead, hang around, and I'll try and remember my main point.
Yeah, it's an interesting point for sure, because it's insane how precise we can measure the universe, which it's just an insane concept to start off with. Like, that's what always fascinated me about cosmology in the first place, is the fact that we can come up with these theories about the universe as a whole. And to get such precision cosmology, and things are only getting better. Like, we have these outstanding surveys that are going to come up with amazing data that we're all looking forward to, in terms of like the large scale structure, and with these surveys called like Euclid, and every other one has just gone out my head now, but there are various SKA and various other cool things, to square kilometer array, sorry for people who don't know the acronyms, and various others, but I do think that we shouldn't kind of cut ourselves short, though, because in the same way we talk about the universe, like one thing that we have been able to do in physics as a whole is come up with extremely precise measurements. Like, in terms of collider experiments, we've been able to make measurements of predictions from our quantum field theory, which I can't remember the number of decimals it is, but for the spin coupling, for G for the electron, we've literally been able to measure that to some stupid level of the level of decimal places. So I feel as physicists, we're just getting better and better at getting these precise measurements. And I think one day, we're going to be able to get this, I guess, more theoretical prediction from the CMB to agree perfectly with what we measure on the sky, And yeah, I don't think we should stop until we've got that, because otherwise, well, we don't really have much to do as cosmologists if we don't. So yeah.
Please be on my grant panel.
So Sean,
I mean, yeah, it is
sorry,
important.
go ahead, Rachel.
Yeah, I was just saying it's super important to note how just dramatically different making measurements out of the CMB and going out and measuring the magnitudes of stars, which is what I do. That's what Henrietta Leavitt did. That's what I still do. Those are just fundamentally different pieces of technology, methodologies, and yet at the end of the day, we're coming out within 2 arbitrary units, kilometers per second per megaparsec. And so there's a great triumph here that often gets lost in the battle between systematics. And so I think that was a nice thing that kind of came out yesterday in our discussion as well.
Yeah, I definitely think that was an important point made yesterday. Sean, you had one point you wanted to make, if you still remember it.
Yeah, I wrote it down. Yeah, I mean, just finishing that previous point. Yeah, we as researchers are so interested in what's broken and what's wrong that's all we spend the time talking about. And maybe to the outside community, we should be a bit more kind of, these are the things that are actually working well. So I just wanted to, my main point was to sort of think about one of the points that Angaran made about tensions going away. So most tensions do go away. And I think the reason why is that when you're measuring lots and lots of things, eventually something, whether it's a small error in the device or a small error in the processing or a small error in the kind of theory of the non-fundamental stuff, that'll become a tension. All of people's eyes will go on that, and then there'll be a lot of scrutiny, and eventually someone finds what went wrong. But tensions don't always go away, right? Like in the late 90s, mid to late 90s, people were measuring the masses of galaxy clusters, and they were just too small. Like, where was the missing mass? Because, is that the right thing? Yeah, because there were indications the universe was flat, and what that means is that there's enough mass that the curvature of space hasn't been overcurved or undercurved. That the way general relativity works, that if you've got more mass, you start to curve space, and so if you have too much mass, you have a kind of closed curvature, and if you have not enough mass, you have an open curvature. Just for the audience, don't worry about the distinction between those two things, but there was an indication that from the expansion rate, there was a certain amount of mass in the universe. But then when we went to measure it by looking inside clusters of galaxies, we were getting too small numbers. So that was a tension that people were worrying about. And then I guess the predecessors to this current Cepheid-based H0 measurement went out and actually measured the expansion rate more accurately, and found out that there was an acceleration, which was indicating that there was a missing component of energy density in the universe, which is what we now call dark energy. And so this anomaly, this tension in the galaxy cluster measurements was actually saying there isn't more mass, there's a different type of energy density. And people who were skeptical in the mid-90s were probably saying, most tensions go away, we'll find out what's going wrong with these galaxy cluster measurements eventually. But no, it was new fundamental physics. So if I was to bet, I would almost certainly bet that this isn't new physics. But I don't think it's completely out of the question that it will be a systematic. But I guess you probably agree with me, but I just wanted to add that nuance.
So I'm very much in the camp of new physics, just because most of my papers have been on solving this H0 tension. So if we suddenly find a systematic, then a lot of the models I've worked on have become meaningless. So I'm also very much in the camp of new physics, just because it's fun and it gives us something nice to play about with. And one thing that really struck me yesterday, so I am a CMB person. I've pretty much always worked on CMB. My plenary talk is about the CMB. And a lot of people in my community have the comment of the local people don't know what they're doing, there's mistakes in their measurement, all these disparaging comments that I'm sure Rachel has heard many times. It's always the idea of they've made some kind of mistake. CMB is perfect. The mistake is definitely on their side. And I think yesterday, just seeing the degree of scrutiny that you all have on your measurements and how you're doing these cross-checks and different teams going through, it really solidified to me the opinion of, I don't think these guys have made a mistake. They appear to know what they're doing, right? And there's so many people working on this that it just it really gives me the impression, and it was reinforced yesterday in the panel session, that actually these local measurements are pretty robust. And I trust them, and I also trust the CMB, which leaves me with new physics. But I'm sure you've heard those comments many times from CMB people, Rachel.
Yeah, no, I just wanted to jump in as well. Like, there have been a lot of interesting papers that have come out, specifically looking at how individual parameters can be what's the word, like not taken into, so like making measurements independent of certain parameters which are used in CMB analysis. So that a few people at Cambridge have done what we call the sound horizon from the CMB. So sound horizon independent measurements of the Hubble parameter from the CMB, and yeah, other various great people at Princeton as well. And literally everything has been dissected in so many different ways when it's come to this detention that that this is talking about the CMB side, but also on the local measurement side in terms of supernovae, Cepheids, etc. Like there have also been various analysis done there. Like there is a huge amount of work that has been gone into, like as you said, cross-checking these things. And every time we do these, there's nothing that comes out which disagrees with it. Nothing that comes out that's really worrying. And like it goes to show just how hard people have like worked in the initial announcements of these measurements. And yeah, the fact that we can come up with these analyses that are like measurement independent of certain parameters, it just goes to show, just kind of is just like a commendment to that fact, I guess. So, but yeah, I'll shut up now.
So, Rachel, there's a very good question here from Paul that I want to ask you. The question is, does the red giant measurement use stars at the same variety of distances from us as the prior standard candle measurements?
Okay, my internet got a little low there, so hopefully this is coming through. So that's a great question. We actually are able to probe very similar distances, but the red giant branch, tip of the red giant branch, is a bit fainter than the mean magnitude, or the typical magnitude of a Cepheid. So we don't go out quite as far, but that's also just a limitation on the time that we've been awarded. If we wanted to go out that far, we could, but you know, the telescope allocation committee has to say yes, it's worth going out to do. And as a result of the galaxies that we've worked with, and with the tip of the red giant branch, and the galaxies that have been worked with Cepheids, there's about 22 or 23 unique galaxies, and we overlap in about 10. And so a lot of our discussion has been about those 10 galaxies where we both can measure distances. And the tricky part there has been that we agree and we're kind of off for others, but we don't it doesn't exactly correlate with some parameter that we could write down. So if it was correlated with distance, or if it was correlated with the fact that this galaxy has this property, then it would give us a huge clue. But so far, it's been pretty random. I'm working on my day-to-day work is a lot of time, is spending a lot of time trying to expand that volume over which we can do these different distances, precisely to make sure that we go out as far as possible, and that we have lots of overlap with different techniques.
I think that was a great question. You mean the one that just popped up from David?
Yeah. That's
okay, so maybe we take this last question from David and then we move on, because we could all spend hours talking about the Hubble tension. So maybe we take this one last question about the panel and then we move on. So Rachel, feel free.
Okay, so the new question that came up was, does the Hubble constant have to be the same value everywhere in the universe, or could it be just different in where we look at these specific objects? So that's a tricky question, because the Hubble constant itself, h0, is literally the value at z of 0. So that value should be more or less the same anywhere we look within this redshift 0 space, within the local universe. However, arguments that, well, if you're in a particularly dense region of space or a particularly underdense region of space, that galaxy or the object there might feel a slightly different expansion. But statistically, when we measure it over the whole sky, we should get the same result everywhere, more or less. And that pretty much has held up for every test that's been done in the nearby universe. Now, a really interesting question is, well, what if the actual change to the Hubble constant is just beyond where we're able to measure? And that would be very convenient of the universe to have tricked us this way. But we also don't think that's the case. The thing is that the Hubble constant at any time z, where z is redshift, but that's also time, is different. We actually know that not only is the universe expanding, it's also accelerating, which basically tells us that the Hubble parameter, which we've thrown around Hubble parameter and Hubble constant a bit, but the Hubble parameter is a function of time, and it is changing over time. So we also know, after we look so far, we're not a straight line, a single value, we're actually that line curve. And that has borne out in lots and lots of experiments as well.
I think that was an excellent question from David. So before we move on, does anyone have a final short comment about the panel discussion yesterday you want to throw out, or are you all happy to move on to the next topic?
I did write myself one little note, which is that it seems pretty clear now that whatever resolves this, it'll either be like new fundamental physics or new other physics. Like it's something that is super subtle that we haven't understood about local astrophysics, perhaps, but it's not just going to be, as Rachel said, some embarrassing mistake. It'll result in new understanding of physics, whatever resolves it. It might be super exciting stuff Deanna works on, or it might be not, but it'll be new.
Yeah, and we should clarify that it's not just a case of throwing in new fundamental physics into the early universe, because it's like a carpet in the room. Like if you change something in the early universe, you end up changing something in the late universe. Sorry, when I say carpet in the room, I mean a oversized carpet in the room. So you just fix a problem in one area, and then something else pops up in the other. So it's not a trivial thing to be just sort of adjusting values to make things work accordingly. And a lot of people have been trying to do this for the past, how long has the Hubble tension been going on for? Like 2 years now? I can't remember.
5, 6 years?
Yeah, as in I mean, there's like
Yeah.
a number of, we've had like a paper a day for like a year or something. It's just so, yeah.
I think that's a good point that we can come back to later, because it ties into one of the parallel sessions we had today. Rachel, any final comments from you before we move on to the next topic? Okay, so that was yesterday. Yesterday was this really long and fun discussion about the H0 tension, and with the format of the conference, and there was plenty of time for us to discuss among ourselves. There were some social games going on in the evening. Honestly, I was too exhausted to participate in the social games yesterday, but there is a lot of activity ongoing. But the main physics yesterday was this excellent discussion on H0, which you can all see we're very motivated about and could probably spend another 2 hours discussing if we didn't force ourselves to stop. But that was one day of the conference. Today we had another fully packed day. Today was the first day we actually had parallel and plenary talks to discuss. So with the conference format, these are talks that we've pre-watched in our own time yesterday, today, over the weekend, if anybody wanted. So today we just joined for the live discussions. We've had 2 plenary talks where the speakers get 45 minutes and several different parallel talks. As the name implies, these take place in parallel, so there's a theme for each one, and you usually choose which room to go in. So today there was a parallel session on large-scale structure, there was one on gravitational waves and the H0 tension, and there was one on the primordial universe. So obviously it's quite difficult to attend all of them, but because we have recordings, we will be able to catch some of the ones we missed as well. But let's start talking about the plenary talks. I believe there was a plenary talk that you were especially interested in, Angaran. Do you want to talk about the plenary talk that you really liked, about the bootstrapping one? Just tell us a bit about this and why you like this one.
Right, yeah, so this is yeah, a really exciting development in the theoretical physics community, and it's done by the likes of Daniel Baumann, Guy Pimentel, and various others in the Netherlands. So Dan Bauman's a PhD students, Carlos, I think Hayden Lee is a postdoc in Harvard, if I remember correctly. If I am getting this wrong, I'm very sorry. But yeah, there's some brilliant people who've just yeah, some very famous theoretical physicists who kind of introduced these ideas back 5 or 6 years ago. Juan Maldacena and Nima Khani Hamed. They're kind of legends in the theoretical physics community, I guess. And yeah, what these ideas are basically saying is that how we normally solve for the early universe is we solve explicit equations for models of what we call inflation. So inflation is this early stage in the universe where the universe expanded rapidly, and from it we get these quantum fluctuations which then go on to imprint themselves on the sky. Either we can measure that through the cosmic microwave background, as we've kind of mentioned, is this sort of primordial soup that like eventually turned into photons that we then measure as cosmologists as the cosmic microwave background today. And these correlation functions, which are basically just differences between different patches on the sky, are also imprinted in what we measure in terms of the structures in our universe and large scale structure. So they're the reasons why you have galaxies forming, because you have slightly larger densities there in one patch of the sky, which then pulls in more matter. And because, as we know, matter attracts one another because gravity is an attractive force. And in other patches of the sky, we have what we call voids, because those are underdense regions. So you don't really have any densities to be attracted towards as a result. And we can actually say things about these specific correlation functions. And I'm trying to think of a better word, sort of I guess like standard deviation, but that's still quite technical. But these comparisons at different points in the sky, just from looking at fundamental symmetries of the space-time that we know exists, or that we think existed in the early universe. And that's what this bootstrap program is doing. Instead of going, I've got these fundamental principles, and then I'm going to apply those to a model and then getting these functions out, I'm just going to use the constraining properties of the symmetries themselves to then determine what my correlation function should be. And it's a really powerful idea, because it allows us access to much more complicated predictions in our observations that we couldn't really do unless we maybe did them numerically. And it's a very exciting and hot topic, because we get a lot from these bootstrapping techniques. And the other exciting development, which is, I guess, kind of interests me in my PhD topic, is that the tools that we use are very like, they sound very exotic and extravagant, like the wave function of the universe. These correlation functions are actually encompassed in what we call the wave function of the universe. And the wave function of the universe is just an idea that, well, quantum mechanically, we know that the universe, well, from our current theories, we know that the universe was quite small, so it must have been governed by a specific quantum theory. And if that's correct, then the way we do quantum mechanics is, or quantum field theory, is that we have these specific wave functions which describe how these states evolve. So by logic, the universe has its own wave function, and these correlation functions can tell us about the nature of the wave function of the universe. And this is interesting for people working in quantum gravity, because solving for the wave function of the universe essentially is kind of like the golden egg that everybody's chasing in that community. So yeah, I hope that was a good enough summary. Sorry.
Yeah, it's a topic that is very far away from what I usually work on, and I've heard a lot of people throwing around the concept of bootstrap, and I've never actually sat down and willed myself to get through a talk on trying to understand it. And the talk we had, or that we discussed today, was actually presented really nicely, and I felt like for the first time I understood what bootstrap is. And I think your explanation there, Angaran, was perfect because it solidified that I did indeed understand some basic things about bootstrapping. So I'm very happy with it. It's a topic that is very far away from me, but it's incredible to think about the theoretical work people are doing to understand these really minute things about the early universe that could have profound implications. So I thought it was a very enlightening talk for me. Sean, I'm not sure if
Yeah.
you've had time to catch up with the talk yet, and if you want to make any comments.
I have actually watched Guy's talk. So you mentioned, I think, Anger and a bunch of people who are working on them. One of them was Guy Pimentel, who was the person who happened to give the plenary talk. So I have watched his talk, but I wasn't there for the discussion. Haven't seen the discussion. I was going to try and do the super ambitious thing of like describing what a 2-point and 3-point correlation function might be for the audience, if people want to let me try that.
Please do so.
The 2-point correlation function is saying, okay, if I have measured a property of the universe here, so for most of this, it's the density of the universe or it's the temperature of the CMB. If I've measured it here, what will that expected or average temperature be at some other point? It depends on the distance between this point and then this point over here. And you then get, probability distribution for what the temperature will be at a certain distance away. And that probability distribution has an average value and as Angaran said, a standard deviation, which is saying how wide the probability distribution is. And it just so happens that because the universe is on average homogeneous and isotropic, so it's the same everywhere and it's the same in every direction, this correlation function really does just depend on the distance. It doesn't matter that I've gone in this direction or in this direction. It just matters that I've gone a certain distance away. And so then that is a 2-point correlation function. The 3-point one is then possibly obvious now. Like instead of I've measured the density here, what is it over here? It's I've got the density here and there's then a conditional probability. What is it here? And given it's this value here and this value here, what might it be at some third value? And the reason that is interesting is as Angaran was saying, it is telling you about the statistical properties of the very early universe and how these fluctuations in the density, the things that become galaxies and the things that become voids were formed. And I think you mentioned that this bootstrapping method takes fundamental symmetries and uses them to make predictions. I thought it might be also interesting to say what some of them are and maybe unpack them. So I remember things like the word unitarity and causality. Does someone want to have a go at explaining what those words mean in a technical sense? I can have a go if no one wants to, but
I'm happy to talk about those. So unitarity is for in a basic sense, it's just basically saying that when we do quantum mechanics, we are actually dealing with probabilities, because as people might have heard in like various like public talks, anything quantum mechanics basically says if something what's the standard line, like if it can happen then it will happen, basically. And that's kind of the idea behind quantum mechanics, is that to interpret that in terms of the trajectory of a particle, what we use is when we use a path integral approach for quantum field theory, is that we say that a particle could take any kind of trajectory to get from this point and this point. Now, obviously, between these 2 points, the most likely trajectory the particle is going to take is probably just a straight line. But in terms of a path integral approach, you could take like various trajectories. And the point is that all these trajectories are given a probability density profile, which is basically just saying they've got a probability attributed to them. And the most random trajectories that you could think of obviously can have a very low probability, but all of these probabilities have to add up to 1, because you can't have those probabilities summing up to something more than 1, because that wouldn't make any sense mathematically speaking. And what that in turn does is that these mathematical objects that we use in quantum field theory are, we call these operators unitary, and that's a specific mathematical property that they have because of the fact that your probabilities have to add up to 1, but without going into bracket notation or this stuff. I think I shouldn't go on too more about unitarity. But then locality and causality. Locality is kind of, I guess, in the name, right? You want your theories to be local, which means that basically one thing that you want things that are local to one another, whether that's in position space or what we call Fourier space. Those things are meant to only be affecting close things. I think in a layman's way of putting it. And then causality that's a hard one. I'm thinking I might leave this one for you, Sean, but
okay. Or if Deanna or Rachel want to have a go, but
Rachel, I think you wanted to give it a go.
Oh, I was just going to say they all seem pretty tough, so did a great job.
Yeah, I'm happy that I'm not taking these questions.
So causality, like the very technical thing, so I'll say this and don't worry if you have no idea what I'm saying, is that things must happen in a light cone, meaning that you can't affect something that is outside this light cone. And what that's meaning in less technical sense is that you can't affect something that's at a very big distance away from you. Yeah, like in a very non-technical sense, it means that there's a cause and effect relationship, that you can't have stuff happening that didn't have a cause. In the sort of intermediate level of technicality, it's meaning that if something is further away from me than, say, the speed of light would allow me to affect it, I can have no influence over it. And there are some models that allow one to kind of go beyond this. But the problem whenever you do violate this causality postulate is that you get all sorts of difficult things to reconcile with common sense. Like the sort of stuff that happens in Doctor Who, where you go back in time and you kill your grandmother, and then, well, if you killed your grandmother, should you exist or not? Like, it just gets very difficult. So the thing I find really interesting, and why I wanted one of us to talk about unitarity, causality, and locality, is that these things just seem so impossible to do without, right? Like unitarity, conservation of probability. I don't know what it means to say that suddenly something has a probability greater than 1. It just doesn't make sense. Causality, it doesn't make sense for an effect not to precede a cause. And what this field of research is doing is saying, okay, let's just assume the early universe has these fundamental symmetries, that it is unitary, that it's causal. What will the late universe look like? And it just seems, as a sort of relative outsider to me, that they're making such overwhelmingly needed and general assumptions that how could they possibly get predictions out at the end? It's like, yeah, the early universe must exist, therefore the late universe has this. You wouldn't think that you'd get anything out of it, but they do. They get all of these predictions that you can go out and test eventually with more machinery about the current universe by making these extremely like important sounding assumptions about the early universe I couldn't imagine deviating from. And I find that fascinating, that on a couple of levels. First of all, that they're able to make these predictions, but then if someone goes out and measures the local universe and it's not satisfying these properties, are we saying that the early universe is somehow deviating from one of these fundamental symmetries? I mean, that would be crazy exciting. Extremely unlikely, but crazy exciting.
Yeah, no, it's really interesting, and like there's actually like work going into the things that we've talked about. We actually understand these in what we call flat space. So when we say flat space, we basically mean, oh, my laptop is dying, but what we're saying is that these are sort of things that basically there's no curvature in the universe. So in the same way, like a black hole curves space-time so drastically, you can't do flat space calculations, but you could do flat space calculations about what goes on in a cosmological colliders, because to all intents and purposes, we're not really near like any sort of extreme curvature. Yes, the sun curves the orbit that we're on, but it's not anything too extreme. But in the early universe, we had a much more different space-time, which we call de Sitter space-time. And basically what we're trying to do now in cosmology is understand how these fundamental principles apply to this very not drastically different space-time. That's one thing I'll get to, but it's a different space-time from flat space, and we've understood flat space very well. Like I was saying before, we know how to do collider physics to extreme precision, we have predictions for parameters in quantum field theory that have been measured so precisely in these colliders. And that's why people talk about the cosmological collider, because we're trying to do the same now for what we call de Sitter spacetime, which was in the early universe. And one really cool thing that people at Cambridge, like Harry Goodhue and Enrico Paia and Sadra Jazayeri, did is that they've shown what the implications of unitarity alone have on these correlation functions, and what they call the cosmological optical theorem. And I find that like fascinating that they've been able to understand unitarity in the early universe to such an extent in this completely alien space-time, and see what these constraining properties are. Because it shows that we're really advancing to the levels of particle physicists in their colliders. And the other thing that's the natural question which might come up is, well, if we understand flat space to such an extent, is there a way of using what we know from flat space to understand what would happen in de Sitter spacetime and from the early universe? And the answer is yes. There's actually been an observation in the fact that we know that these correlation functions in flat space look very similar to the objects that we have in this de Sitter spacetime. And a recent paper by Guy and Daniel Bauman's group is that you can actually use these functions that you have in flat spacetime. You can actually hit them with an operator, which they call lifting, to go from flat space correlators to the de Sitter ones. And I find that such an amazing, like, remarkable advancement, because it's relating these two seemingly completely different space times. Well, they look mathematically similar, but we've never really been able to wrap our heads around how to relate them. But we're making progress into actually showing how they could be related. And I feel like I'm going on for ages, but yeah, I find that kind of beautiful in a sense.
I think that was an amazing summary. I thought it was a really good talk. Just before we move on, Rachel, do you want to add anything to what's already been a very intense discussion on this subject? Okay, so
no, we're way out of my wheelhouse. Yeah.
Yeah, it was definitely a very technical topic, and I think you guys did a great job of breaking it down to an understandable level. And as I mentioned, the speaker of the plenary session also did a very good job with this. So we had one other plenary talk today. This was about large-scale probes of the early universe by Azadeh Moradinazit. I'm sorry if I mispronounced that name. It's my first time attempting to pronounce it. I will try better next time. But we had this second plenary talk, which was a really cool idea of using large-scale probes of the universe, like everything that happened in the so-called Dark Ages, which is a big part of the universe that, as the name implies, we can't see. It's in between the time of the CMB and when the first stars began to form. There's no light there, so we can't really measure much. But it's using information from this era to try to understand what happened in the very, very, very early universe. And it was completely fascinating to me to see how they related this. So who would like to give a few more details about this session? Angaran?
Yeah, I thought I'd jump in. So there was a lot of interesting discussions about the nature of what we call primordial non-Gaussianity. Without sounding too trivial, what non-Gaussianity is saying is our deviation from Gaussian conditions. Oh, I forgot to charge, put my laptop on charge. Sorry, 2 seconds. Basically, what we use to measure PNG, I'm just going to use that acronym because it's so long to say primordial non-Gaussianity, it's a measure of this 3-point. It's something related to this 3-point function that Sean described very well just a few minutes ago. Basically, this area of research is showing is how we can go about measuring specific like shapes of this 3-point function. So as Sean said, you've got this 3-point function on the sky, and it can have different shapes, and this can show us so many interesting insights into the primordial universe, just like the actual shapes of what this could be, because you can have the standard equilateral shape, but then it can take up like an isosceles triangle, for example, or a scalene one, and you can squish it and play around with it in various different ways. And what this talk was addressing was specifically how we can go about measuring these. And yeah, I guess I'll leave it to other people to kind of talk more about the like line intensity mapping stuff and skew power spectra.
There was a question by Christian here in the comments about something you said. What do you mean here by Gaussian conditions and by non-Gaussianity? Do you want to just elaborate?
Yes. Yeah, so when we say Gaussian initial conditions is so we say that when we say Gaussian, it means that everything follows this kind of like bell curve probability, and I guess the point is non-Gaussianity is something that deviates away, and that's just that's not very hoping is there can anybody else kind of think of a way of describing non-Gaussianity without thinking of bell curves?
I can have a try. I mean, bell curves is what Gaussian is, right? So a Gaussian distribution is something that says all of these correlation functions. Because if you remember, I was saying that the correlation function is saying if I know the density here, what's the density here? It's got some probability distribution. Well, that probability distribution is a Gaussian one. So it's a bell curve, or if people want the mathematics, it's e to the power of minus x squared with a bunch of factors that are constants. And then the 3-point correlation functions are also Gaussians. If I have this density here and I've got the conditional probability here, that's a Gaussian. And then if I've got this one and this one, what is this one? That's also a Gaussian. It's all Gaussians. Everything is Gaussian. It's just one very, very big multivariate Gaussian distribution. Everything that depends on everything else has that bell-shaped curve. So yeah, as you said, Angaran. What was that?
We like Gauss because mathematically they're very convenient.
Well, but there's also very good reasons to think that the early universe was Gaussian, which we can get into in a second, or at least very, very close to Gaussian. Right. So deviations from Gaussianity, like, I mean, I think you're feeling Angaran like you're not explaining it well when you say it's just not Gaussian, but that is actually the best answer we can give, because there's a continuous infinity of ways you can not be Gaussian. I guess what you're feeling a little bit unsatisfied about is that there's specific types of ways in which the early universe might deviate from Gaussianity that you kind of want to explain. So I think the mathematics here is maybe simple enough that you can actually say it. There's a type called local non-Gaussianity, which literally just means the mathematics behind that would say, take every point in the universe, take its Gaussian probability distribution and add that value squared. And it's local because it's happening locally at every point in space. It's non-Gaussian because the Gaussian has been squared. Not the Gaussian distribution, but the value of the density. So that would be one of the types of non-Gaussianity. So every time Angaran would say non-local, that's what, local non-Gaussianity, that's what he would be meaning. And then if you wanted to talk about the equilateral one, I think you can also define that quite easily. It's that you get these triangles, right? Like the 3-point function is in physical space, but actually that one will be kind of tricky because you have to define it in what you were saying as Fourier space. So I'm not going to be able to do equilateral off the cuff, unfortunately. The local one is easy, but equilateral is more difficult. Sorry, audience. But Angaran, maybe have another shot if you want.
There's also another comment that we can just pull in again from Christian. He says he understands what we mean about Gaussian non-Gaussianity. How do you know that the distribution is Gaussian and not other statistics?
Right, that actually just comes from our theories of the early universe, basically. So basically from the fact that we even other theories predict these Gaussian conditions, but the inflation, which is known as being our concordance model, I guess is the right word, or like the accepted general theory for current cosmology, predicts this Gaussian distribution of fluctuations in the universe. So that's why we think it's there. And also we've measured it. So
and it predicts it because it generates all of these distributions by taking what is a quantum mechanical ground state and stretching it. So and it so happens that the quantum mechanical ground state solution, if you just have a potential energy function, which is a quadratic function, which is the simplest one you can write down, because if you don't have the quadratic term, then you have a linear one, and then your energy density will just roll down to negative infinity. So the simplest one you can write down is a quadratic, and then the solution to that happens to have a Gaussian distribution, that the energy density sitting inside this well will have the Gaussian shape. It wants to be at the center, and as you move away, it goes down. Yes, quantum mechanics is the reason.
Yeah,
the ground
basically
state of the early universe is Gaussian, and inflation doesn't mess with it much.
That's kind of our get out for everything, right? Because quantum mechanics, that's just our answer for everything.
Yeah,
but saying it that way makes it sound like it's sweeping under the rug. The solution
but
of the ground
usually
state
true.
is Gaussian. Sure,
yeah, no,
sure.
But to quote Weinberg, you can basically model the whole universe as I'm paraphrasing him, but yeah, you can model the whole universe as quantum harmonic oscillators, and yeah, those things give us Gaussian statistics. So that's just basically all that's happening. So, and yeah, as we discussed, we think that the universe was governed by quantum mechanics because we think it was very small. So yeah.
So maybe so that we don't stay here all night or all day for Sean. Any final comments we want to do about the second plenary before we move on? If anyone has any other comments to make here.
Maybe just one quick comment that if we were to measure any of these non-Gaussianity parameters, how cool that would be, because it's then directly telling us something about the early universe. I mean, I think As It Is talk was kind of a observational version of Guy's theory talk. Like, how do we actually go out and look for these interesting types of correlation functions? And it would just be awesome. Like, it would be one of the most profound things humanity's ever done, because there's lots of interesting stuff we've learned about kind of our universe and the early universe being the CMB, but this would be learning about the early universe. It would just be amazing.
Yeah, it's in we should reiterate how much effort was taken into getting the 2-point function right. So it took a lot of time and a lot of effort to get it to like the precise measurements that we got with Planck, which was the data was released in 2013, right, and been analyzed since. And we knew about the cosmic microwave background all the way back to Penzias and Wilson, which was I don't know, the dates escaping me. I think there's something like the 70s. So it took about 50 years to get the 2-point function. To now try and do something even more difficult, the 3-point function it will be a massive step forward and an amazing achievement. But there are also other probes that we can use for the early universe, which is something that we might start discussing now. I don't know, but we can use these recent advancements in gravitational wave detectors. So we can essentially measure the 2-point function of how what we call tensor modes should hopefully, which we're hoping to find in the cosmic microwave background. And so yeah, not like non-Gaussianity is not our only probe of these the early universe.
It's just looking for my mute button again, or my unmute button. Okay, so I think it's been a very excellent discussion about the second plenary as well. They're very complicated topics, and I think we're doing a good job of explaining them in ways that are a bit more understandable. And this is also honestly great for me to review everything that I've learned today, so this is super nice. So these were the 2 plenary talks that we had, but we've also, as I mentioned, had the first session of parallel sessions today, the first group of parallel sessions. We had one session on gravitational waves and the H0 constant. I was very happy that the organizers put my 2 favorite topics together. We had a session on large-scale structure, and we had a session on primordial universe. In each of these sessions, there were 5 talks with an upper limit of 20 minutes. I've watched some of the talks in the large-scale structure session, and I watched all of the ones from gravitational wave and H0. And one overall thing that has struck me is how creative people are being with their talks, right? Because this is a 20-minute pre-recorded talks. For my plenary, I did the basic thing of sit in front of my Zoom, sit in front of my computer, put on Zoom, slides on one side, me in top right corner, record. And we're getting people here adding soundtracks and taking us around a tour of the city while giving a talk. Absolutely incredible. I'm loving all of the creativity coming out from all of the parallel talks that I've watched so far. There have been some really excellent ones, and I like to see this. It's definitely a fun thing this conference has added. And I think very briefly, I just want to make a comment from the gravitational wave and H0 session. I think one of my takeaways has been how good we're getting at finding new ways of testing ourselves. Because almost all of the parallel talks I've seen have been like, here's a new mechanism, here's a new procedure, a new method. And it's not just reinventing the wheel or redoing what's done. It's like, let's do this in a completely different approach and see what happens. Let's try something brand new and see what happens. The amount of innovation that I've heard about in these parallel talks today has really stood out to me. So move on to everyone else. Rachel, I'm not sure which session you attended, if you were able to attend one of the sessions.
No, sadly, I've been catching up on other work after my session yesterday, so I'll hand it over to everybody else.
Yeah, and I think for Sean, it's a bit too early in the morning for you to have been able to catch up, because we finished these like an hour before you got up, so that was 5 a.m. your time, so a bit too early. But Angaran, you were in the Primordial Universe session, I believe.
Yeah, so yeah, there were loads of interesting talks that were going on, and actually it kind of gives me an opportunity to kind of elaborate on some stuff that I've hinted at, which is that although inflation that we've sort of accepted as a community is probably the right theory. Okay, I might be speaking on behalf of too many people in that front there, but it's I would say the majority of the community are in favor of inflation for this early universe theory, and the alternatives to those were brought up in this primordial universe parallel session, and that's quite an interesting topic as a whole, because there are various models which can give us, as we said, these Gaussian initial conditions, and or like what we call the scale invariant spectra perturbations from the early universe, and that's one of the I guess like crowning achievements of inflation from the 80s. But other theories have shown that they can do the exact same, and this came up in the primordial universe parallel discussions because we've got these other models from very famous scientists. So the recent Nobel laureate Roger Penrose has this model called conformal cyclic cosmology, which it's not as developed as a theory, but it gives an explanation for why the early universe looks the way it does, and spits out certain prediction in terms of what we call these Hawking points in the sky, which is essentially just the evaporation of these supermassive black holes at the end of what we call an eon. So you match the cosmic microwave background's emission to the end of a previous universe, and you have what we call these conformal rescaling. So that was one topic which was covered, and another one which was covered was this idea of string gas cosmology and bouncing universes. These are other alternatives to how the early universe could have started. So bouncing cosmologies, for people who don't know, that these are universes which are also a sort of cyclical model, but instead of you just having expansion as the only sort of process for the universe, you have a contracting universe going into an expanding one, and essentially they bounce at the singularity. And these theories are interesting because a lot of the predictions that they give are the same as inflation, and they give a lot of the crowning achievement predictions of inflation, but they haven't been given as much attention because they have a lot of problems which are seen as more difficult to overcome than those problems that we have with inflation. So, but there has been a lot more attention towards these theories recently, I think, or maybe it's just sort of like the similar amount of attention. I'm just reading the literature more, but yeah, these theories are quite interesting. And then the other stuff that came up, I feel like I have to summarize quite a lot because there's various discussions. But
yeah, maybe in the sake of time, just like highlight what you thought was best that came up, just because elsewise we will be here all evening.
Yeah, exactly. What was best that came up, I guess, was the idea of what I mentioned before was string cosmology. String cosmology is in a sense is just basically predicting what string theory as a quantum gravity theory would expect the universe to do, right? And string cosmology actually has a very interesting idea. So some of the predictions that you find, depending with how you kind of work with these string theories, is that you can actually find a duality between these theories. So between an inflating universe and a bouncing universe. And it's something that's always intrigued me because there are certain theories that show us that actually inflation and the de Sitter spacetime that I described inflation's model by is actually not consistent with some of these quantum gravity theories. And we're a lot of quantum gravity theorists really do back these theories for good measure. So the idea of a duality between the two could be an explanation for why you have something that looks like a de Sitter inflationary universe, but in actuality was something like a bouncing universe. And that's a really exciting idea, I think, and something I'd like to look into more.
Yeah, that sounds very interesting. I will go back and watch some of the talks for that session as well. I think one takeaway message from me, because we had the gravitational wave and H0 session. So as you've already heard today, H0, the Hubble constant, is a topic that we can discuss about a lot. There was one talk that was coming up with new ways of testing our standard lambda CDM cosmology or our standard model of cosmology, and kind of new consistency checks that any other model would have to satisfy to still be accurate. So one of the main takeaways from this specific talk was raising the question of, would a modification of early universe physics be enough to solve the H0 tension? The answer that was discussed in the talk was no, this is not going to be enough. And the speaker, Sunny Vagnosi, actually ran a poll to see what the audience thought, and almost everybody consistently voted no, this is not going to be enough to solve the tension. So I thought that was nice. I also like the incorporation of the poll to see in general what the community is thinking about this. So that was definitely a talk that I thought was very interesting going forward. But really, all of the parallel talks I attended today were excellent. All of the discussions were really good. In the sake of time, we can't talk about each one of them individually. But if any of the speakers are watching, if we didn't mention your talk, it's really not personal. It's just because else we would be here all day if we had to discuss every single talk. So if there's nothing left to mention about the parallel sessions today, I think we can wrap up our discussion of what we've experienced so far in the first 2 days of the conference, and maybe just move on to what's coming. What are we looking forward to? What are we excited about this week? And Sean, I'm going to start with you.
Sorry, just finding the unmute button. Yeah, like, so the thing I'm most excited about that's coming up, I forget whether it's in week 1 or week 2, is the eROSITA telescope's plenary talk and following discussion. The reason I'm very excited about this is eROSITA is an X-ray telescope who have a telescope in space that's measured the X-ray signal from all sorts of different directions. And they released their data either the last week or the week before. And then we're the first conference that has had them present with their data released and able to talk about it. So X-ray telescopes can do lots of stuff. So I think most of the useful stuff for it will be on the more astrophysical side. And for a cosmologist's interest, it's kind of just setting the background parameters better so that we can do the cosmology better. But there's some stuff that X-ray telescopes do that is directly relevant to cosmology and super interesting. For example, measuring the centers of clusters of galaxies and thus knowing the masses of the clusters of galaxies better. That's one example. Also, indirectly from that, you also measure how much ordinary matter there is in the universe, which plays a very crucial part in things like the CMB. So it's an independent measurement of this parameter, how much hydrogen essentially there is in the universe. So what I'm really excited about, and hopefully someone will be talking to you guys about this next week, maybe, is what the cosmology will be able to be done with these new results from eROSITA. They themselves haven't written any cosmology specific papers yet, but I'm sure there are cosmologists who are just crazy excited about being able to use this so that they have a catalog of galaxy clusters. I know that for sure that they have measured, and that will be used for cosmology. So yeah, I basically, I'm blathering on a bit because I don't know what the results will be, but that's why it's exciting, because in a week's time I will know what people have been saying. So I'm really looking forward to that.
Yeah, that's definitely a highlight. Rachel, what are you looking forward to the most in the coming days of the conference?
So far, I've really enjoyed the ability to go in depth a great deal. I think that's something enabled by the way the in-person parts are going. And so for me, as more of a true astronomer who dabbles in cosmology, I learn how to think about cosmological problems and how to adapt my way of thinking from astronomer land into something that's more rigorous and statistical, and learning methods and what to do. So it's kind of a ding that I give it a lot. But I also learn how to make arguments in this space too, which is useful. And I try to bring that into my work. I'm speaking the same language. So I like the way the interactions are going, because I learn more of the language this way.
Nice. And Goran, what are you looking forward to in the next few days of the conference?
I don't know if I would say I'm nervous about tomorrow, because we're actually planning to have a themed discussion about the sort of so this is, I guess, like a more non-physics topic, but it's very important. Is the challenges that PhD students and other academics generally face inside and outside of research, and I'll be speaking with a few others about it, and yeah, I guess that's definitely going to be a very honest and hopefully like productive discussion. And then on top of that, there's definitely various like areas which I'm interested in, which I'm kind of looking forward to kind of getting back into. So I did my master's in more modified gravity stuff, and I'm looking forward to hearing more talks in the sort of advancements and that have come about in that field. And modified gravity, for the non-experts watching, is it's basically just us trying to work out if there's any changes to general relativity, which is the currently accepted theory, that could potentially describe the universe and various other sort of like phenomena better than general relativity, without sort of messing up the things that general relativity does really well.
Nice. Me personally, I'm actually just going to do a bit of self-promotion. I'm looking forward to Thursday, because it's when we have the discussion of my plenary talk. Now that we finished the discussion of the first talks, I imagine the questions are going to start coming in. And this is my first plenary talk. So I'm really excited to see what kind of questions people have come up with, see what people are going to throw my way. And I'm very excited to listen to the other talk in my session, or in the same time slot as mine, which is on other CMB missions. People know that I love the CMB. And there's going to be a talk about Akatama and the South Pole Telescope. So I'm really excited to listen to those as well. And another thing I'm super happy about is how much outreach we have planned for these 2 weeks. I say we, again, I'm not an organizer. I'm just jumping in on all of the outreach I can. So I believe, correct me if I'm wrong, Sean, but there's going to be another recap one day this week. Still not clear on the date. At least one, potentially more if we get more people interested. And there will be a live Ask Me Anything. I believe that's going to be on Friday. Next week would be the same idea. So a couple of recaps and an Ask Me Anything on Friday.
Yeah, so the Ask Me Anything on Friday will almost certainly be at 7 p.m. UTC. And there'll be a corresponding Reddit AMA if you prefer writing it in text and having people answer in text. And then, so there will be another recap like this, probably in 2 days, possibly at exactly the same time, or at 1 hour later at 7 instead of at 6. This one started at 6.
Yeah, so we have a lot more conference outreach to look forward to, a lot more days of conference and sharing the conference with all of you. And now, just before we wrap up, I want to allow everybody here on screen to talk maybe about stuff that's not conference related. If there's anything else you want to mention or want to tell us. And Grant, let's start with you. I know there's something you want to tell people about as well.
Yeah, no. So as we've been talking about, there's some great outreach initiatives going on with this conference. And I think, yeah, I would like to take the opportunity to talk about an organization that myself and a few other fantastic individuals have started. So this organization is called UniArc. So UniArc, yeah, just UNI, and then capital ARK. I think I'll put a link in the chat soon. But UniArc is an organization that's specifically looking to help students from advantaged countries and backgrounds and persecuted communities to access top tier education in the UK, US, Europe, etc. And myself and others, we are looking to help these students for free get into these universities. So not only just get successful applications, but also try and help them get funding for these universities, because obviously these kinds of degrees don't come cheap for international students. And yeah, I just want to use this opportunity to spread the word about UniArc. And yeah, no, thank you so much for giving me the opportunity to share about that. I'll put the link in the chat for anybody who wants to help us, because we're still looking for volunteers to either mentor or just generally help with the administrative side. But yeah, we're off to a good start. But obviously we will take all the help that we can get, because we, as I said, we're doing this for free. This is a completely non-profit organization, so there's no money going into my back pocket. I can promise you.
Yeah, it's definitely something worthy of bringing up. So thank you for sharing that with us, and thank you for your work on that. Okay, Rachel, anything you want to tell us about that is not conference related? Oh, I think we just lost Rachel. We've lasted most of the broadcast. Sean, anything non-conference you want to tell us about?
No, not today.
Okay. Rachel, I think we have you back now. Any non-conference things you want to tell us about briefly before we wrap up?
Yeah, so I'm part of this little project called the Sloan Digital Sky Survey, and we are happily putting together the final data release from SDSS 4. It won't go public until December now, and we're pretty excited to be bringing that to the world in a couple of months, and it's a very intense time for us right now. But yeah.
Okay, we're looking forward to the new results. That's going to be great. Okay, so let me say a big thank you to everybody who joined here on screen. It's been great to have such a good discussion about the conference. And of course, thank you to everybody who followed along in the comments, who sent in questions, who made nice comments, and of course for the awards. As you heard, there will be more live streaming events happening in the context of this conference throughout the week. Now, I know you're used to seeing me on HAPS when there's Cosmology. I might not be in all of these events, but I will be popping up in and out. But do make sure you follow everybody here on screen, just in case everybody starts their own broadcasts. And make sure you follow the main account here, the Trenches of Cosmology, which is where you're going to find all of the live stream events for the Cosmo from Home conference in the coming 2 weeks. Okay, so if any final comments from anybody, now is the chance.
Other than to just more visibly thank Deanna for hosting the conversation. I wrote a comment, but I'll also say thanks.
Thank you.
No, thank you so much, Deanna. If it just for all your work is inspiring. The amount of outreach and stuff that you do. So thank you.
Thank you very much, and I hope to get you all back on HAPS again very soon. In the meantime, we hope everybody stays safe. Take care of yourself. Sean, you can end the broadcast when you want.